We have 1 minute to go. I think more participants will join in the next few minutes. I'm very happy today to have Moritz in the cohort presenting you ELISE, a low-code platform for every engineer, which can accelerate product development by 10x, as he says. So big claims, but I hope Moritz will clarify that during the talk. Yeah, Moritz, over to you, and enjoy the show.
Yeah, thanks, Jousef, for the invitation, and yeah, welcome everybody. From my side, I'm Moritz, one of the co-founders, managing directors of ELISE, and I'm based in Germany, north of Germany, sitting in Hamburg today, and I have my roots in South Germany, near Stuttgart, a little town called Heidenheim, where I grew up, and then like did some like studies in Stuttgart, which I was trying to get yeah, some aerospace knowledge down the road. So I was studying aerospace engineering, and it was like yeah, a couple of last lessons that I basically heard a professor talking about the idea of yeah, biomimetics, so the idea of how to copy nature and bring it to the engineers in order to innovate solutions. And it was something which somehow fascinated me as a student, because so far I only knew those very boring sheet metal designs or U profiles that we had to figure out. And bionic was something like out of this world. It was these like real organic shapes and innovative material properties. Yeah, so I decided to dig a bit deeper in this area and went up north to Bremen to do my PhD in this area. And I was focusing on more or less the methodology, how engineers develop hardware products. So all about product development processes, methods and tools, and how you could perhaps come up with a, let's say, more innovative approach on how to develop hardware. And yeah, this was now, well, roughly 20 years ago that the journey started, where I also met my startup team at the research institute. And yeah, here we are. Now we are a startup called ELISE. We are around, as I said, Jousef, 40 to 50 people at the moment in Bremen based, so north of Germany. And yeah, it's super happy to have the opportunity to tell you a little bit about our software, about our startup, and glad that yeah, some of you joined here in our room. If you want, you can definitely turn on your cameras or ask questions over the chat functions, or just hop in if you have any questions. I guess we have roughly like 1 hour together. So I'm gonna present you a little bit of the history about the motivation, why we like came up with the low-code platform for engineers, about our background. And I've also prepared a little demo for you today to give you some ideas about how the software looks, what you can do with it. And by tomorrow morning, also Marvin, my co-founder, will hop in and give you a nice introduction so that you can have like the software tried out by yourself. And yeah, get your hands dirty on it. So what do you think? Shall we jump right in?
Let's do it.
All right. Yeah, Jousef already said it. It's about low code, and it's about accelerating product development by the factor of 10x. And yeah, this is like our claim that we said, well, the current capabilities of engineers, how they develop parts, should be accelerated, not only by 10% or 100%. No, it's like 10 times the speed that we want engineers to develop products in the past. And this is, of course, a huge claim, but I hope that after our session today, you might understand why we think that this is feasible and possible, and also might be something which you would like to dig a little bit deeper in your studies and your engineering career later. So yeah, as I said, we started as a research institute down the road in 2008, then founded a company. And I guess before actually being able to found a company, we have been doing basic research over 15 years in total. at the so-called Alfred Wegener Institute. It's a climate and polar and marine research institute of north of Germany. And the interesting thing is about this research institute, it's that it has nothing to do with techniques or with engineering at all. It's basically a biological institute where people try to understand our climate or try to understand why some animals live on the planet. And there was like one specific animal, or I would call it an algae, which interested us most. And this algae was called diatoms. I guess some of you might have heard about it. It's a one cellular algae which is living in the oceans. You can like, if you go swimming in the North Sea, for example, you will get thousands of them into your mouth. And this algae is very specific and very special for us, because this algae has like a cell, and the outer cell, like an exoskeleton, is based in a very dense and hard, like defense structure. And so the biologists were asking themselves, why is this algae basically protecting itself so much? And on the other side, the material that this algae is using has a more density than water. So if the algae would just put enough armor on top of it, it would just sink down to the bottom of the sea. And as it needs photosynthesis for getting energy, it will not survive. So the basic idea was that in nature, there is a kind of an arms race against defense structures and aggressive structures who want to eat the algae. And during evolution, basically nature had found some optimal shapes in order to protect the algae from getting eaten by its pretenders. And so this idea was like the fundamental question, or could we mimic those arms race and convert it to the engineering world? And we tried to do this. We tried to build up optimization loops between parametric CAD models and crash analysis tools, and tried to rebuild nature. And during that time, we realized that the tools that engineers usually are used to do, like classical CAD tools, are not very sufficient in order to get this job done. And so from this very early date, 2018 then, was a big milestone for us. So we tried to bring our own engineering tools to the market and funded a company. And now, as you can see, we are like a VC backed. So it's like a venture capital game that we are playing, among others, by, for example, Spark, who is the investor of, or one of the first investors of Twitter and also Slack. We have like UVC and Sherry, former Zalando founders on place, also Venture Stars, and also BMW iVentures is one of our VC. And so I guess it's a very good setup in order to give customers, like, for example, automotive industry or aerospace industry, a software solution that they are now using, not anymore to do these bionic designs, which we did in the past, but to do like optimal hardware development. But the same principles are still there: optimizing parametric designs, keeping operations loops between CAD simulation, FE simulations, and to automate these tasks. So it's been a long journey, but we have like one vision in mind, and we think this is something which really like is a red line from the red stroke from the very beginning until now, that we think that the way how we develop technical parts at the moment need to somehow change fundamentally. Because at the moment, what we do as engineers is we draw, for example, sketches by hand, or we simulate with manual meshing stuff, these kind of stuff. And we think in the future, this is not efficient anymore. And also it makes no fun, to be honest. So we want to have a future of engineers where we basically work hand in hand with smart algorithms, maybe AI or intelligent algorithms, so that we as engineers are able to really develop products better and faster. So this is the goal that we have. And as ELISE, we want to be a small like software tool to support this vision, to really enable engineers to work hand in hand with computers. And this is the basic idea behind the software. And the question is, of course, why do we think that intelligent algorithms or automated designs enable engineers to do such a big leap in the product development? Well, if you have a look into, let's say, software development, not sure if maybe some of you already had some website programming in their past, or had done some website programming, maybe some HTML cracks among us here. At least I was like doing website design before even I go to the university. And that during that very early days time, I need to write code. So I needed to write HTML or CSS or PHP code line by line. And if I now look in our website, which we are building right now, things changed a little bit. So nowadays we have those frameworks or libraries like WordPress, HubSpot, Webflow. Like these are like frameworks which include the basic functionalities of the code. So nowadays, I would say even my mother could come up with a nice software design or website design, even if she could not actually write code herself. So there has something changed in the software world, and we are able to really like do all those great website designs without writing any line of code. But in the hardware development, it's still like these early days in software development. If we would come up with let's say a design of a B pillar or anything, any product, we would still need to draw the sketches by hand, set up the models by hand. So there is still this early day in hardware development. And the fundamental principles, how we are using state-of-the-art software development, is not there in hardware development. So we believe that there needs to be, or there's huge potential in bringing in these methodologies of software developers into the hardware world. And that's basically what we try to do. So not sure if some of you already had done some engineering projects in your like student projects or maybe on your free time or in your internships. But I tried to, let's say, summarize how engineers typically like are doing engineering at the moment at our customers, for example, at BMW or at Mercedes. And what we see is a huge fragmented ecosystem of different software tools, each for a specific job to get done, but each maybe from another software vendor or from another, with another user interface. You can see Hypermesh, real like powerful tool with an old style user interface. Then we have maybe Excel, one of the beloved software tools from engineers, definitely. We have those CAM tools in here. And basically, whenever like a product is developed, it needs to be like converted from one software to another software and back again to come up with these iteration loops in order to like come from a design to a simulation to maybe some manufacturing manuals. And the whole ecosystem needs somehow to be in line, needs to be connected. And the interesting thing is that once like a project is finished and there's maybe a change in the design, or you need to develop another part which hasn't been developed before, engineers typically start from scratch. So they go back in the CAD world, do a whole redesign, then doing back the meshing because the mesh properties are lost and stuff. So it goes on and on and on. And this is a huge problem at the moment in our in the engineering world in general. So we see that we have this like status quo of doing engineering, but we also see that we need to be faster in time to market. So as you see, for example, with our climate crisis, which is coming up, people need to reinvent sustainable cars or electromobility, and they need to do this fast. So the time of actually being able to explore different variations to see which is the best best solution and to drive this development process really fast to a final product, this is crucial. And at the same time, we have this huge problem, or at least like the demand, that we need to increase the complexity as well. So we need to think about recycling, we need to think about CO2 footprint, we need to think about multi-material designs, like all the complexity that comes into those systems, at the same time being fast in development. Those two drivers, they really crash if we are using these old processes, methods, and tools of development. And there are also some little side effects that also our customers are telling us, and which are, I guess, good for you as young engineers, but also for the companies, it's kind of really a challenge at the moment, that those very experienced engineers, if they get retired, basically, the knowledge is lost with them. So the experts, for example, if they leave the company, they're just like taking the knowledge with them, and it's not available for the company anymore. And all of these drivers, they lead to a single question. And we've asked this, like our clients, do you think that it is enough to actually just get faster, or just to hire more people, or to like do the engineering offshore in, let's say, India or something? And all of them said like the same thing. No, actually, if we would solve like these problems of the future, we need to rethink how we develop products, how we actually like do engineering in general. And we need to be not only like 10% or 20% faster, no, we need to be like 7 or 10x faster. And so yeah, we have been naive enough to let's accept the challenge, and we tried to come up with a solution that in the early days at the research institute helped us to build up these biomimetic evolution games, and in the new world could also help engineers. And so what we have like done is that we have found a solution how we can actually like save roughly 80% of the development time. So this is like 8 or 9x in the development. Some projects even like 12x in here. And we have done this now for roughly 4 years, testing, doing like the use cases at our customers. You can see some among them, like Airbus, for example, or BMW, or Hyundai, Safran for the rocket launchers in here. So different industries, also washing machines, for example, are among them. And on average, it's roughly those 76% of time saving. And this is interesting because usually if you think about just getting faster, it's not enough. So we have to change fundamental principles. And one idea of what we actually changed is that we say, well, engineers, once they set up a project or set up a workflow, as we call it, they should never start from scratch again. Because this is actually what happens nowadays if you develop a part or a product. So imagine you are developing, let's say, a Volkswagen Golf, maybe now in the 8th generation, and you develop the platform with all the efforts of your engineers. So this is like 3 to 4 years, the full power of your engineers in there. And then the platform is released. And if you then want to develop the next generation of the Golf, what actually is happening is that you start from scratch again. So maybe you have some takeover parts that are just copied, but basically the whole fundamental principle, the baseline of the structure is a new project. And once this is finished, you again start from scratch. And this is something which we think should change fundamentally. And we think there should be something more like this, that you have like a project or task that you do. And once it's finished and you want to redo it, or you want to adopt it, or you want to optimize it, you should like start from exactly the same level that you already have developed. So we call it that engineers should be able to store, to share, and to reuse their work. And this is something which is super interesting, because in the software development, this is already the case. So for example, if you ask Meta, I guess they are called now, how they are developing Facebook, for example, in the version 23, 24, 25, they never start from scratch. They always optimize the code base, which is in the book, and optimize it. So it's a system of continuous improvement. And it's a system of taking the things that you already have and optimize it. And actually, that's what we're doing. So the question is, how is this possible to have hardware development with the same methods or frameworks like software development? Well, the answer is quite simple. We need a programming language. So we need a language for engineers that they can write code. And I'm not sure if you can write code. I can do a little bit of VBA maybe and some macro scripting, but I'm actually not a programmer. So for me, it's super hard to do this programming. So is it for most of the engineers? And so we decided to invent the first visual programming language for engineers. And yes, you can see it here in this boxes. I will also show it to you in a second in live. These are like building blocks, and we can wire them up to create algorithms. So it's like it's a low-code language, we call it, because it's not like real writing code. It's more like a visual code language, but it's super easy to use. I guess also you get a chance tomorrow to get your hands on to try it out for your own. And with this low-code language, we are able to come up with, we call it workflows that connect different tasks. So this could be either creating a geometry, or this could be running a simulation. This could be like integrating an existing software tool. This could be optimizing a loop or running a topology optimization or integrating AI models into a workflow. So all the different like tasks that usually engineers have to do, they are somehow like available with these very easy to use building blocks. And one of the main like aspects of the software is that it's an open ecosystem. So we think that engineers should be able to select the tools that they want. So maybe if you want to do like crash simulation, you should be able to choose between PamCrash and LS-DYNA or Radius maybe. And that's why we think having these like open system where engineers could connect their software tools in one environment might be a good solution. So yeah, the basic architecture of our program, as you can see it on the right, is has like 3 areas. There's the platform, which is like the low-code editor that you're using. And then we have some, we call it like the standard components. Or no, it's like the logic editor, the CAD editor to create geometry, the simulations editor, or the optimization loops, optimizer. And then we have the third-party plugins, which you can just also use. So for example, from Altair, the Hypermesh solution, or from Hexagon's generative design solutions. And this setup is really smart, as you are able to connect basically everything that you want. And if you are ready to program, you can also integrate your Python code and stuff. So it gives a nice development framework to play around. And also the ecosystem that we are like providing, and I guess you also will have the chance to test it out later. It already like connects a couple of different software vendor tools, and you are free to select those, choose them, and plug it into your workflow like you want. So this was like a first stretch, some theoretical background information. Are there questions already here that I could answer before we just like jump into the software itself?
I guess not, Moritz.
No questions. Okay.
We're all a little bit shy. We're engineers, Moritz.
You can also write the questions in the chat if you're not do not want to raise your voice. But then let's just have a look into the software. I guess then maybe the one or the other question might arise. So as you can see, can you see the software, the 2 gray screens?
Yeah, works.
Perfect. So this is the software, this is ELISE. And I want to give you a short introduction to it and guide you through, show you 1 or 2 examples before I then go back into the PowerPoint world to show you some like what our customers did with it. But you can see that it's basically divided into these two areas. We have on the right side here, we have our CAD environment, where we will see the geometry erasing in a second. So this is something like you can think about having like an output, for example, for a CAD model for the algorithms, and also like the interaction with the geometry world. And on the left side, we call it like our virtual canvas here, where we are able to do the visual programming now. And I want to start with a very simple example, just by taking two variables, maybe a 6 and a 7 in here. And I would like to connect those two to a node which does multiplication for us. And if I give you the answer to all of the questions 42 here, it's just like the multiplication of those two numbers. So this is the basic principle of how the software works. So information is always flying from left over those wires to right. And we have those components which are like doing something. In this case, a very simple mathematical multiplication. We have inputs on the left and we have outputs on the right. And over those wires or cables, there could be any information flying. So in this case, it's super simple. It's an integer value, a number, 6 and 7. And now if I change the parameters, maybe to 4, you can see that also the downstream results are updated instantly. So in this case, it's 4 times 7 is 28. Or if I change this on the background, it's 24, 4 times 6. I guess you get the idea of how the system works. And the interesting thing is that we can now use this principle of visual programming for lots of different tasks. So this was maybe a hop into here the world of, let's say, math. You can see that we have lots of logic operators in here. So for example, if this is larger than that, or gates in here, or modulus, or divisions, or here's our multiplication component. But we also can do all the MATLAB style field-driven designs, tensors. So everything that you would need to come up with logic or mathematical expressions could be programmed in here. But also we can do, let's say, more geometric stuff. So for example, creating points or curves or lines. So now we are more in the area of the geometry generation or CAD modeling. And this is where things get really interesting. Oh, my internet connection is unstable. Can you still see me or hear me?
We can see you, but I think voice is a bit broken.
Also hear me?
Yeah, right now it works.
Okay, then let's hope that the internet connection stays like it is.
Yeah. Moritz, we have maybe one incoming question that you could answer. How is ELISE different from the cloud-based software like Fusion 360, where the designs are shared with the team members in real time with version and revision numbers automatically?
Yeah, good question. Yeah, so Fusion 360 is still, I would say, a classical CAD software tool. So you still create geometries by hand with sketches, and then it's there. And if you want to connect it to, let's say, another software tool, you need to write, I know, scripts or integrate it into optimizing tools. So the software that we're having here is not cloud-based, so it's more like a Windows application. But you can connect, for example, Fusion to have your CAD model done. I guess we will show this in a second. If we also go to my next example where we like connect the CAD processes to the FE world, then I hope it should get clear that we have more like I would say more a process software here in ELISE and not the design software. But maybe you can re-raise the question after the live demo. Let's see if I could answer it. So what I want to do next is maybe hopping into the geometry world and creating a, let's say, for example, a sphere. Now you can see that on the right side, there is the geometry appearing. And if I click on the sphere, I can see the building block who generated the sphere. And if I now connect, for example, the result to the radius, I will have more like a parametric geometry here. So I have like the possibility to manipulate my geometry. And I can do this with all the surface designs, the geometry world, but I also can go a little bit further. Let's say, for example, to the meshing world and create like a geometry mesh in here. So now I can see that the geometry type switched from NURBS modeling to a mesh design. And you can see this component here is doing basically a body input where a geometry is running over the wire, and that the output here, for example, you can see that it's a mesh container. So we have roughly 2,000 vertices and faces in here. So we can like manipulate data among different, let's say, geometries or meshes. And the next step then, if we go a little bit more down into the engineering rabbit hole, would be something like simulation. And there I've prepared a little example for you, which is basically a very simple bending beam, which you can see also on the right side. You can see it's like a geometry, like a box in here. And yeah, now let's just follow those wires here, what happens. So first, the geometry gets inputted into a component, which is a solid mesh component in here. If I turn it on, basically you can see that we are able to mesh the geometry. Now we are defining the boundary conditions for a finite element simulation. So the mesh inputs into a part. We have the material definition. We have the support, the forces in here. We have a static linear load case connected to a complete model. And if I now, let's say, have a look into the model, you can see that we can do classical like FE pre and post processing in the software. So I can see that here on the right part, we have those nodes that are constrained in all the degrees of freedom. And we can see that the forces are like tearing down on the side of the bending beam. And now I want to like have a little bit of a look into the support definition, because now things get interesting. Because here the support basically, as you see, is defined by a rule. And this rule is that the support should be applied to all geometries that are in this plane. And if I like turn on the plane, you can see that all the nodes that are inside of this plane get this constraint. But now what happens if I, for example, enter like a tolerance of, I don't know, maybe 5, plug it in here. Now you can see that instantly these boundary conditions got applied to even like larger area. And this is something which is really new to engineers, that we can apply also like the finite element boundary conditions rule-based. So not based on geometries, not based on the mesh, but on rules. And now this enables us to do something really interesting. So let's run the finite element solver here. You can see the result of this bending beam. Yeah, you can see like the stresses. We can also switch to the displacement maybe. And you can see like the colors here of the beam. And so far, I would say this is also possible to set up in, let's say, Fusion, for example, for the CAD part, and then maybe like connect SimScale or another cloud simulation tool with it to run these simulations. But what we have built here is not, let's say, a model for this one bending beam. So in this area, the whole process world here, we have created a set of rules how to simulate any kind of bending beam. So you can see, for example, if I'm going back again to the geometry and just like maybe grab this wire or this point here, which like defines the bending beam length, and just like make it a little bit longer. So I'm taking this node and just dragging it to make it a little bit longer. Whoop, and it's resimulating. So the whole process gets more or less like automatically redone or resimulated. Let's do it again. You can see it. And the interesting thing is that we have like created a, more or less a workflow on how to simulate those bending beams. And this is, I guess, the difference. that we are not looking into, also this happens from time to time, that we are not looking into, let's say, a single bending beam or process. We're looking more on a set of rules on how to create these bending beams. And this was like a very simple example, but I want to hop next to a, let's say, more like real case, which we are able to show. It's from one of our customers from the Japanese automotive industry. And it's about a, we call it a steering knuckle. So it's a, I'm not sure if you have heard this before. It's a part of the car which connects basically your wheel and the chassis of the car. So with the braking caliber and everything in there. This will need a couple of seconds to load the whole process, but I guess you get a real insight into an example how this looks like in the real world. And what you can see here now on the left side is basically a end-to-end development process for an automotive part. And all of these different colors that you see here are different departments usually. So just like very high-level workthrough, there's at the very beginning of a design project, there might be some managers who are defining the requirements or the, let's say, the basic ideas on how big, how fast the car or the steering knuckle has to be. And then there is maybe an FE department, then there's a simulation department, maybe you have like a design department, you have again some managers or some manufacturing guys, and at the end you need like to export your final data to the printer or to your manufacturing machine. And all of these different colors that you can see here on the left side usually use a different set of software tools. So let's have a look. Maybe the product manager at the very beginning, who like gets, for example, the geometry from a design space. So maybe he gets like from his managers the design space where the project or the geometry could take place. He gets the interfaces of the car from a packaging designers. He also maybe gets all the possible materials here. You can see this is like from an Excel list in here. So let's maybe open such an Excel list to see what's in there. Where is it open? Excel. Yes. So it's basically the whole material database of this client here. With usually material properties, strengths, densities, and all the stuff that an engineer needs. Let's see why my Excel is not running. Maybe needs a couple of seconds. It also needs like the loads in here. So we see that we have the whole target stiffnesses of the part. Also, all the requirements that basically are required for developing this whole product are in here. And now these information, as you can see, they are going to everywhere in the process. So the whole design team needs these informations, and the information is flying and flowing from department to department. And we also have like the first department here, which is, for example, the FE department who is creating the simulations. Or if we go a little bit further, we have the simulation department who is doing the stress design. And for me, always very interesting is to see this specific step here, where we need to have like a topology optimization in the process. So maybe you have heard about this design principle. It's the idea of like finding the optimal load path and design inside of a design space. And you can see that the neutral axis of this part is more or less deleted, and you can see where the material distribution should be placed from a mathematical optimum. And with this information, usually there's like again, maybe in Fusion, some guys who are like trying to redesign this process. And the problem is usually something like this here. You can see that there are little fragments, or there's like this tessellated designs, and you need to interpretate this world. And if you are looking into a process view like this, we might be able to, let's have an algorithm which tries to like do a little bit of cleaning in here to come up with a quad mesh instead of a tria mesh, then going maybe into some technology which we call the topology reconstruction. It's the idea of having a subdivision technology to create a NURBS geometry out of it. And all of these steps, they look here like very simple. So it's like one component. But maybe you have realized that I can like also look under the hood of this workflow. And if I click on it, I get the sub workflow. You know, this is really interesting. It's going a little bit into the details of the software, but it is the basic principle of having, let's say, functions in software code. So imagine again, bringing my example from the very beginning, that you want to come up with a website and maybe you need a login function. But a login function is something which is really standardized. So you can use a login function for any website. And the same goes with our function approach here. In this function, for example, somebody has coded the rule set on how to come from a mesh back to a geometry world. And this function could be not only used in a single project, it could be used basically on every project just by copying and pasting this workflow into the next project. And this thing goes on. So in here, for example, we go to the production area. So it's like a 3D printed part. So there is a component which, for example, calculates the whole print job. So you can see that if I want to print this thing, basically in my build shop, I can like put 6 of these parts. You also can see that the red areas here, they need some support for the printing process. So you can see like the support structure in here. Yeah, so you get like a cost report, for example. In this case, it's 21,000 euros, the whole build shop, and it's 3,500 euros. Also what you can see in the dashboard for the manufacturing cost for one of these pieces. And this is basically the idea of the process. So you get the full access to everything what you would like to know about this part. And again, we have designed, or the customer of us here has designed this workflow. So it's not about actually having like this single steering knuckle design. So if I now go back, same thing like if I change the length of my bending beam, and if I reconnect, let's say, the big design space, which might be from, let's say, a Volkswagen Passat, the big car, and we want to change it to a Volkswagen Golf, I can just unplug it and re-plug it into the maybe smaller piece. And now the process is rerunning. So let's see where we are. You can see that the yellow components, those ones, they're somehow outdated, so they need some information. And we are at the moment, the process is running here. And now the topology optimization is running. Then the CAD design is running. I can loop in, you see also like the time that it needs for calculating the stuff. And if we wait now a couple of seconds, we should see the new design of the new smaller car, and we should also see the new costs and the new part weight. And now, I guess this is something which is really at the core of our software, that we are not developing a single part, but we are more or less designing a set of rules and processes and steps how to design a part. And for usually the setup process of such a thing takes a little bit maybe longer than doing it manually in the classical CAD tools. But once the process is there, and once you have to redo the thing, or you have to optimize it or to run iterations, you really can save 90% of time, 96%, 99% of time. And this is our like also the basic idea how we save 10x or how we accelerate product development by 10x, because we are just digitalizing all the things, all the tasks that you need to do in order to come up with a part like this, and afterwards could automatically run it. It's just an amount of computational power that you need in order to define or speed up your process. but all the knowledge of the engineers, every decision, every line and every like process is coded in this visual programming language. And I hope this also answers a little bit your question, Murad, about the difference between Fusion and ELISE. We are more like this process digitalization engine, and maybe Fusion could be, for example, used to generate, let's say, the initial design here. So we have, for example, also possibilities to import from CATIA or to from Siemens NX or other Parasol kernels. And I guess Fusion is also based on the Parasolid CAD kernel. So we could possibly like import the geometry if you want to do this, and then further process it down the road, for example, to connect it with other tools that you might need for a product development process. Cool. So far with the live demo, I hope you get a little bit of idea what we're doing and also what you might be doing tomorrow. I know that there was a lot of detail here. Marvin and the team will guide you through the very basic principles tomorrow. But I think, yeah, you could get like a nice understanding. I want to show you my favorite component here. Let's see, where is it? It's a component from Hexagon called Emendate. Not sure if you might use it later. It's a topology optimization component. And the great thing about the software is we have these nice example files coming with every component that you can have a look at, which give you like a minimal, basic idea of how the function works. So you can see here, it's already running some topology optimization here. And this is like again, a very simple bending beam. And now you can see live here how this component is trying to optimize the structure to find a real lightweight design. And yeah, I guess this is something which makes fun to work with. And also you might have the chance to use it in the tutorials tomorrow. Cool. There's another question coming in. Also, yeah, if you're replacing Teamcenter, most likely not. So Teamcenter is more a database where geometry is stored and versioned and updated. And we will come up with a connection to Teamcenter, also to Windchill and to Aras and the other things, maybe also to GitLab, where you can do the versioning and the stuffs in the external software. So I think we are like complementary to those systems, as those systems are really big databases, and we are more focusing on workflow automation. I'll stop the solution here. Yeah. Are there other questions to the software? Yeah, actually, that's a good one. So ELISE has been a Grasshopper plugin in the past. So we have our roots of being a Grasshopper user. We love Grasshopper in the community. And we asked also McNeil if they want to like work with us together and create a Grasshopper for engineers. Because the Rhino CAD kernel was not really feasible for engineers, as there is no solid modeling in here. And so, yeah, McNeil was very happy with being in the architectural world. And so we decided to basically create nothing else than the Grasshopper for engineers. So if you have like experience in Grasshopper and you're an engineer, I guess you will love ELISE. It's yeah, we tried to copy the best things that we love from Grasshopper and improve the things that we were annoyed. Multi-threading and these kind of stuff, some parallelization. So yeah, it's basically the same. Good question.
Nice. Really cool demo, Moritz, by the way. Really nice. I think the best way to actually learn ELISE is to actually really use it live. So tomorrow there will be a live demo session actually. Marvin showing you ELISE, working through a use case, and then you'll also get a homework in ELISE. That will be fun.
Exactly. So then
any more questions, guys?
Okay. Then let me maybe show you a little bit some of one or two like use cases that our customers have done, which will give you an idea how you can use the software. So this is an example from from Airbus. They have done a kinematic part of an A320. And we try to compare the, let's say, the old world with the new world. And what you can see here is that Airbus at the moment is using like 9 different software tools and iteration loops, certain iteration loops. Among the software tools, it's usually like CATIA as a CAD tool, Nastran for the simulation world, Excel, and also the HyperWorks suite, and OptiStruct for the solver technology. And as you can see here, they're doing classical engineering iterations, 30 in a row, in order then to optimize the part. And if you compare the solution where they did develop the same part with ELISE, you can see that basically they were able to like automate their iteration loops and therefore save roughly 90% of the time. But also, which is interesting for me as an engineer, is that they were able to optimize the final outcome, the weight. And we asked those engineers at Airbus why. I mean, of course, we're optimizing stuff, but we're not changing really the tools and the things. And I would expect that the engineers at Airbus will also be able to reduce the weight. And we asked them, why did you like come up with 200 grams at the end? And they answered us, well, to be honest, we had a budget and a time. And after 640 hours of like doing these iterations, we had to take the best result that was on the table. And this is something which really like I didn't expect from them to answer. And it shows that if we are using algorithms or computational power to run, I know, maybe like 10,000 design iterations overnight, it gives us not only the opportunity to be faster, but it also gives us the opportunity to explore a wider design space and really to choose the optimal design. And this is something which I really like about the solution, that it gives us the flexibility to just play around, explore stuffs, and search for the optimal solution. And I guess it's not limited to the aerospace industry. Also, like automotive industry is using the software. This is a part from Hyundai. It's a B-pillar design. It's in the iconic here on the B side, on the B pillar. And for this part, what me really interested is that it's a highly like secured part and a crash part, because at the B pillar, it basically protects you as a passenger. So when there's a car accident and it's like crashing to the side, this is really where the energy is absorbed. So a really complex part. And usually those engineers, they said, well, if we are able to save, I don't know, maybe like 2% in weight, or if we can come up with a, let's say 2 or 3% more energy absorption, this would be a great benefit for us. And unfortunately, we're not able to show the real numbers, but if you can see here, the energy absorption or intrusion factor coming from 100% to 80, this means that we have like 20% more performance in the part. And so this is a complete other level than just optimizing the part. And this was possible because we explored, I know, like 10,000 of different parameter sets in order to come up with the one final parameter set, which was able to really like absorb so much energy. And maybe another example, my last one, which I also like, is from the space industry. It's from Ariane. They're doing like the Ariane 6 rocket, and there it's a thermal problem which they have to solve. It's a bracket which they optimized also for 3D printing for the latest launcher technology. And also here you can see that we were able to, on the one hand, like fully automate the process. So this is really nice because they do not have only one bracket. They have, I don't know, 3-digit amounts of brackets, and every bracket could be now fully generated automatically with such a process. But also, if you look into the weight savings coming from roughly 700 to 300 grams, this is really huge for space applications because every gram is really like super expensive payload. And if you're able to optimize performance and simulation time at the same time, this is a great thing. And I'm really looking forward to your feedback if you're using the software on your own and try to get these things going. So I think
sorry, but I have a question, please.
Yeah.
Can you please return to the software, please?
To the live demo?
The software, yes.
Yeah.
Where you did your simulation.
Yeah. This one?
No, I want to see the first, the example where you changed the geometry.
Where it changed it now? You mean the simulation example or the
About knuckles? I don't know. Where you changed the geometry from bigger one to smaller one.
the steering knuckle.
Yeah, exactly.
Yes. So yeah, this process. Yeah.
I didn't understand what did you do exactly. So first you changed the geometry because I don't know exactly what is that steering knuckle. Because I don't know a lot about cars. So you only changed the geometry.
Yeah.
And you keep all the other blocks the same.
Yeah. Exactly.
So no need to change anything in the boundary conditions, for example, or in the values of some parameters, for example, in the other block.
They're changed as well. So here, for example, these are like the different materials, and you can see that there are like two inputs. Here we have a stream filter, which is a logic that like also switches like the material.
So you did some change. So you did some changes.
Yeah.
In the other blocks, but you didn't show us that.
Yeah, sure. So for example,
okay.
for the smaller steering knuckle, you might have other forces. For example, it's a smaller car. You might have other forces reacting on the wheel. Maybe it's a smaller wheel. So usually in the real world, it's not only changing boundary conditions. Usually if you have derivates, so different variations of a part, there are also like let's say the forces or the materials or the manufacturing technique changes. But it really depends on what the project is about. The beauty of such a system is that you can like really define your own logic. So for example, if you can read from an Excel list here, or here, for example, where are the material models in here? You can do like a mass of multiplying things and saying if this, then that, or so. So you can be really creative in setting up these logics. And usually this is what the project managers can do. So the people who know basically what kind of materials or what kind of loads are required, they can set up the system.
Okay, sorry. So you need always to do some changes in the blocks.
If it makes sense from a mechanical point, you don't need to. But for example, if you only want to change the geometry, you can rerun the process with the same parameters, only to change geometry. But the question is if this makes sense in the real world later. So if you would, for example, apply the big forces from an SUV to a small part of the car, which is made for, I don't know, maybe a small car, it might explode or something because it's just like too much force.
Okay, I understand. And also I want to ask this software, can we use this software, for example, for CFD problems?
Yeah, we're working at the moment with these CFD connections. So it's not yet there. At the moment, if we go to the finite element models, we can do linear static, modal, nonlinear, and buckling. So I would say like the mechanical simulations.
So it's more for mechanical engineers.
Yeah. So
for cars or Airbus or aircrafts. Yeah.
Exactly. But we also have some customers who are like using the software to do the pre-processing for CFD simulations, for example, like the meshing and the geometry generation, and then scripting the CFD solvers. So if you are using maybe OpenFOAM or something like this, we have this nice component which is called Run External Program, or in the release which will come out next week, We have also some web components. So if you have like a cloud software tool, like for example, SimScale, you can just like connect the software to the API of this tool and use the CFD capabilities from the external software. So that's on our roadmap, but at the moment it's focused on mechanical engineering. Yeah.
Yeah, okay, I understand. Thank you.
You're welcome. Yeah, so as I said, what's next? I guess we said it a couple of minutes ago. I guess all of you should have received your login credentials to log into our portal via email. So you can log in under elise.de and also download the software directly. And Marvin will guide you tomorrow through the whole installation process and getting you the getting started courses ready, so that you like to come in very easily into the software, start small, and then make great things afterwards. Maybe even some CFD simulations, Rima, if you would like to do. And we also would like to invite you to just like use our support if you have any questions. Also, Marvin will tell you how to do this. We have very experienced customer success engineers who are really open for questions and try to give you a best experience that you could imagine. So yeah, from my side, I guess this was like a short introduction into the world of connected engineering. I hope you have a nice start tomorrow with the software to try it out on your own. And yeah, if you like it, or even if you don't like it, even better, we would highly appreciate to get some feedback of you, what we could improve, where we are missing some things, also maybe on the onboarding material. As you know, we are a startup, so we are eager to learn. And people who are using the software for the first time are the best feedbackers. So highly welcome to just like drop me a line, Moritz at ELISE.de or Marvin at ELISE.de. I guess you can use all of the channels that are available, and just like have fun.
Great presentation, Moritz, as always. Actually, Max wrote me a couple of minutes ago, so you should have all received your credentials to ELISE. So feel free, please, to download the software and install it before the tutorial tomorrow. If you just want to follow along with Marvin tomorrow, just follow along. And if you have any issue with the license, I guess Marvin at elise.de is the email address to go. Perfect. Moritz, really much appreciated. Hope to talk to you soon, hopefully in person.
See you.
That would
Jousef,
be amazing.
for the invitation.
Sure, and
good evening.
See you soon. Bye-bye.
Bye.